Usually when we talk about a company reaching the absolute pinnacle of its industry, like
Right.
when we talk about total market dominance, we expect a very specific kind of narrative.
Yeah, visionary product or something.
Exactly. We expect an iconic brand logo that everyone recognizes on the street. Or maybe, a direct, unbreakable emotional relationship with the everyday consumer.
You think of the smartphones glowing in our hands, right?
Right. Or the high-powered graphics cards rendering our video games.
Yeah.
Even the massive server farms quietly running the entire internet.
Absolutely.
The underlying assumption is always that the most valuable, most important player in the game is the one whose name is printed on the glossy box.
It's just how we're conditioned to think about business.
But what if I told you that the single most important manufacturer in the entire global technology ecosystem achieved that status through a completely different, almost paradoxical strategy?
Uh,
What if they conquered the industry by actively, stubbornly refusing to ever make a single product of their own?
it is arguably the ultimate paradox of modern capitalism. I mean, in an industry utterly obsessed with being the star of the show, this particular company looked at the landscape and chose to be the stage.
Wow. Yeah.
And by making that very deliberate, highly disciplined choice, they didn't just build a successful business, they built a structural choke point that the entire digital world now depends on.
No choke point.
Yeah, a repository of manufacturing intelligence that no single competitor can match.
Well, welcome. We are so glad you are joining us for this custom-tailored deep dive. We have a genuinely fascinating mission today.
We really do.
We are unpacking a highly detailed analysis of how one specific company, the Taiwan Semiconductor Manufacturing Company, or, better known as TSMC, took what sounds like a massive strategic concession and turned it into the greatest, most impenetrable information moat we have ever seen in the business world.
And our goal for you today is to understand not just the timeline of how they did this, but the actual underlying mechanics of their absolute unwavering neutrality.
Because it's wild. It just flies in the face of everything you learn in Business 101.
Right. But before we get into the details of this strategy, I want you to visualize the physical backdrop of what we're actually discussing.
Okay, set the scene.
Imagine a vast, dark, cavernous, clean room cathedral. The air is filtered to a degree that makes an operating room look dirty.
Like, completely pristine.
Exactly. And right in the center of it, suspended and moving along an automated track, is a luminous, mirror-like silicon wafer.
Okay.
If you look closely at the reflection on that polished silicon, you don't see one corporate brand.
We see everyone's brand.
Right. You see the faint, anonymous silhouettes of almost every major technology company on Earth. Apple, NVIDIA, AMD, Qualcomm.
All of them.
All of their microscopic engineering decisions, all of their distinct architectural leaps, they flow physically through this one neutral factory.
So today we are going to connect the dots between pure business strategy, flawless manufacturing execution, and the immense, almost suffocating weight of global geopolitics.
It's a big web.
I am genuinely so enthusiastic about this because, like I said, it just goes against the instinct to always own the customer.
Totally.
But before we can truly appreciate the absolute genius of TSMC's model, we have to travel back in time. We need to understand the constraints of the semiconductor industry prior to 1987.
The straitjacket of the old world.
Yeah, the straitjacket. We need to understand that before we can appreciate the Escape Act. So let's explore that era. What did this old, vertically integrated world look like before TSMC came along and flipped the entire table?
Right.
Like, exactly what did it take to be a chip company in, say, 1980?
Well, to understand the magnitude of the disruption, you really have to feel the constraints of that specific era.
Okay.
Back then, the dominant assumption, the unquestioned rule of the industry really was that if you were a serious chip company, you had to do absolutely everything yourself.
Everything.
This was known as the IDM model, the integrated device manufacturer. Think of the legacy giants like Intel or Texas Instruments.
Right, the big guys.
Yeah. If you had a brilliant idea for a cutting-edge chip, you couldn't just design the circuitry on a computer and send the file off to be built by someone else.
You couldn't just outsource it.
No, not at all. You needed to physically build your own fabrication plants, which are called fabs. You had to hire legions of your own chemical and process engineers.
Wow.
You had to manage incredibly complex relationships with the companies that built the specialized equipment. You had to run the entire manufacturing organization from the ground up.
So design and production were just fused together.
Exactly. Design, which is fundamentally a creative and architectural pursuit, and production, which is fundamentally about heavy industrial chemistry and physics, lived under one single, massively expensive roof.
Okay, let's unpack this for a second, because I want to make sure you, the listener, really grasp how restrictive this is for human innovation.
It's huge.
It feels like we were talking about a brilliant author who has a masterpiece of a novel in their head.
Ooh, I like this analogy.
Right, but they are legally or structurally forbidden from publishing that novel unless they also personally own a printing press.
And manage a paper mill.
Exactly, and run the logging company that chops down the trees to make the pulp. It's an insane barrier to entry.
It really is.
If your genius is writing a story, why on earth do you need to know how to operate heavy industrial logging machinery? You are filtering out massive amounts of talent just because they don't own a factory.
That analogy perfectly isolates the first major structural flaw of the IDM era. It was a profound economic flaw, a massive barrier to entry.
The cost.
The cost.
Yeah.
The capital required to manufacture chips started to divorce entirely from the creativity required to design them.
Because fabs aren't cheap.
Building a fab isn't like building a car factory. We are talking about facilities that require their own dedicated power substations.
Jeez.
Water purification facilities that process millions of gallons a day to a level of purity where a single speck of dust is a catastrophe.
Just one speck.
One speck. As these fabs became astronomically expensive and as the process complexity of shrinking transistors exploded, the financial realities shifted entirely.
Great. So a brilliant design team of, say, 20 people might know exactly what the future of computing looked like.
They might have the blueprints for a revolutionary architecture that could change the world.
But if they couldn't secure the hundreds of millions and eventually billions of dollars required to finance and operate the physical manufacturing machine.
Oh, they were completely locked out. Their ideas just died on the whiteboard.
I'm going to pause on that phrase you just used. The process complexity of shrinking transistors. Let's demystify that for a second.
Sure.
When we talk about shrinking transistors to these microscopic levels, what are we physically doing? Because I think people hear technology and just assume computers magically get faster.
Right. They think it's software.
But this is a physical constraint. Imagine trying to draw a highly detailed street map of New York City. Every avenue, every building, every alleyway.
Okay.
Now, imagine trying to draw that entire map on the surface of a postage stamp. And the pen you are using is so small that the ink is quite literally made of individual atoms.
It's mind-boggling.
If your hand shakes by the width of a single molecule, you wipe out Broadway. That is the level of physical precision we are talking about when these IDMs were trying to manufacture chips.
Right. The physical reality is actually even more extreme than that.
Wait, really?
Yeah. You aren't just drawing a map. You are building a three-dimensional city on that postage stamp.
Oh, wow.
You are layering conductive materials and insulating materials, etching canyons and building microscopic bridges.
Unbelievable.
You are dealing with quantum tunneling effects, where electrons simply jump across barriers because the walls are too thin. You're pushing the absolute boundaries of material science and applied physics.
So when you bundle that brutally difficult physical reality with the completely different discipline of software and logic architecture...
You create a system under immense stress.
But wait, let me play devil's advocate here for a sec.
Go for it.
Didn't that integration make sense at the time? I mean, wasn't it necessary to have design and manufacturing under one roof to ensure quality control?
In the beginning, yes.
Especially back when the technology was in its earlier stages. And maybe the communication between the person drawing the blueprint and the person running the machine needed to be incredibly tight.
Yeah.
Like, if I am pushing the laws of physics, I want my engineer sitting right next to my designer.
You hit on the exact justification that kept the IDM model alive and dominant for so long.
It wasn't just foolishness.
No, not at all. In the very early days, when the economics were smaller and the technological frontier moved a bit more slowly, it did make a certain kind of sense.
The designers could literally walk down the hall.
Exactly. Grab a coffee and talk directly to the fab engineers about a yield issue. The feedback loop was contained.
Right.
But that model inevitably broke down because the technological frontier didn't just advance, it exploded in complexity.
The two curves diverged.
The sheer physics and chemistry required to etch those microscopic pathways became so specialized, so financially demanding, that bundling it with chip design became economically irrational.
You had two completely different evolutionary curves Design innovation and manufacturing execution shackled together.
Yep. If your design team had a bad year, your multi-billion-dollar factory sat idle and bled money. And
Ouch.
conversely, if your factory fell behind on the physics, your brilliant designers were trapped selling inferior products.
And beyond the sheer cost, there was a second massive flaw hiding in that old structure, a flaw built entirely around trust.
Or rather, the complete lack of it.
Yes. Let's say you were one of those smaller, brilliant design teams. You didn't have $1 billion.
Right.
So you scoured the market and managed to find an IDM, a giant merchant manufacturer who happened to have a little bit of extra space in their factory this month, and they agreed to print your chips for you for a fee.
You lived in constant paralyzing fear.
Because they are your competitor.
Exactly.
You are essentially handing over your most valuable proprietary blueprints to a company that might decide to just steal your architecture and launch their own version tomorrow.
It goes right back to your printing press analogy.
Yeah. You're handing the manuscript of your brilliant unpublished novel to a printing press owner who also happens to write and sell competing novels.
Of course they are going to read your manuscript.
Of course they are going to steal your best plot twists.
And because of that totally justified fear, the industry lacked a genuinely neutral manufacturing layer.
So the whole system was just stuck.
This meant the Fabless model, a company that only does the creative design and outsources the factory work, was functionally impossible to scale.
The trust simply wasn't there.
If you had a great idea, you couldn't risk giving it to Intel or Texas Instruments. And without trust, the entire ecosystem was stunted.
This was the massive blind spot of the 1980s tech world.
The industry didn't just need more factories, it needed a fundamental unbundling of invention from production.
But it needed to happen without destroying the economic incentives for either side.
Exactly.
Which brings us to 1987. The tension in this broken, untrustworthy, overly expensive IDM system is at an absolute boiling point.
Ready to snap.
And it sets the stage for a radical intervention. Let's shift our focus to Morris Chang, the founder of TSMC. Because he didn't just tweak the existing system, he completely inverted the underlying philosophy.
He really did.
And he was uniquely positioned to see the flaw because he had lived inside the old system for decades, right?
Yeah, Morris Chang is a fascinating figure because he wasn't some outside startup guy throwing stones at the establishment. He was the establishment.
Hey, he was on the inside.
He spent a quarter of a century at Texas Instruments, rising to the very top ranks. He knew the IDM model intimately.
He knew its strengths.
And more importantly, he saw its breaking points long before anyone else did. So when he was approached by the Taiwanese government to help build their semiconductor industry, he looked at the landscape and asked a conceptual question that no one else was asking.
He didn't ask, how do we build another chip company to beat Intel?
No. He asked, how do we build the manufacturing institution that every chip company can trust?
Wow.
He realized that Taiwan couldn't compete on design. The US and Japan had a massive head start. But he saw that graveyard of brilliant unfunded design teams.
He saw the pent-up demand for a manufacturer that wouldn't steal ideas. That shift in perspective is wild. Instead of trying to win the game by playing the same rules as everyone else, he decided to build the board that everyone else has to play on.
And he enforced this vision with an absolute ironclad rule. Looking back at TSMC's pivotal 1998 annual report, the company explicitly stated that its charter fundamentally prevented it from designing or making its own branded integrated circuit products.
They put it in writing for the world to see.
We will never compete with you. We are a pure-play foundry. We are your partner, your quiet engine, not your rival on the store shelves.
But I really have to push back on this, because knowing how hyper-competitive the high-stakes tech world is wasn't leaving the branded product market seen as a massive concession at the time.
Oh, absolutely.
I mean, the real glory, the famous logos, the massive consumer markups, that's all in the branded products. You don't see kids lining up around the block to buy a TSMC wafer.
No, they line up to buy an Apple iPhone or an NVIDIA graphics card.
Right. So weren't they essentially looking at the most glamorous, high-margin money on the table and just willfully walking away from it?
It looked exactly like a concession to the traditional legacy players. They thought Chang was building a low-margin commodity service.
Like just a dumb pipe.
Exactly. But this is the genius of the insight. Neutrality was not a weakness. Neutrality was the foundational edge.
Because it removed the fear.
Yes. By defining their entire corporate identity by what they would never do, by swearing off competition with their customers, TSMC created perfect, unbreakable incentive alignment.
Think about the psychology of that.
The designers desperately wanted the best possible manufacturing, without fear of intellectual property theft. TSMC desperately wanted the highest volume of diverse designs to keep their incredibly expensive factories running at maximum efficiency.
So they needed each other.
This alignment liberated the ecosystem.
It created this concept of the virtual fab.
The virtual fab is the turning point of modern computing. TSMC essentially broadcast a message to the world's brightest engineers. You focus entirely on architecture. Focus on system design, on graphics processing, on artificial intelligence algorithms.
We'll handle the heavy lifting.
We will handle the brutal, capital-intensive, balance sheet-destroying nightmare of running the physical plant. We will deal with the toxic chemicals and the billion-dollar lithography machines.
And we promise to be so perfectly integrated with your software that it will feel exactly as if you own the factory yourself.
Precisely.
And that single insight is what paved the way for the fabless revolution. Firms like NVIDIA, Qualcomm, and Broadcom companies that dominate our world today could suddenly flourish.
Out of nowhere.
Right. A guy like Jensen Huang at NVIDIA could start a company in a Denny's diner, focusing entirely on the math of 3D graphics because he didn't have to raise $5 billion to build a chemical plant to print his chips.
TSMC democratized the physical layer of the internet.
Here's where it gets really interesting for me, because we've established that they built this foundation of absolute trust. They made the promise, and they kept it.
It absolutely did.
But trust isn't just some feel-good metric for a corporate brochure. In this specific scenario, trust became the raw input for a massive compounding intelligence engine.
Yes.
What happens when literally everyone in the industry trusts you to build their stuff?
What happens is you build a flywheel of accumulated knowledge that is virtually impossible for any vertically integrated company to catch up to.
It's an unstoppable force.
The analysis breaks down this massive learning machine into 4 distinct layers, and the first layer is pure aggregation.
It is all about the sheer scale of the data flowing through the clean rooms. Let's talk about the data because the numbers here are staggering.
Go for it.
In 2024, advanced technology, which is defined in this context as 7-nanometer process nodes and below, made up 69% of TSMC's entire wafer revenue.
Over 2/3.
Right. And in the fourth quarter of 2024, high-performance computing and smartphones hit 43% each.
Wow.
That means 86% of their total net revenue for that quarter came from the absolute bleeding edge of human technology. They aren't just making cheap chips for microwaves.
Those numbers prove a critical point about their positioning. TSMC does not just sit somewhere in the middle of a mundane supply chain making generic commodity parts.
No, they're the vanguard.
They sit squarely at the absolute frontier of human engineering. And the scale of that aggregation is immense.
Give me the numbers for 2025.
By 2025, TSMC reported serving 534 distinct customers,
Okay.
manufacturing 12,682 different products.
Wait, I need to stop and process that. 12,682 different products.
Yeah, 1 year.
If you run a normal factory, say, a car factory, you make maybe 3 models of a car. Retooling the factory line to make a new model takes months. How on earth does a company swap a manufacturing line between 12,000 different microscopically complex designs without the whole system grinding to a halt?
They do it through an intense standardization of the interface between design and manufacturing.
How does that work?
TSMC provides its customers with what are called process libraries and mask services.
Okay, let's get an ELI 5 on those terms. What is a mask service?
Think of a mask like a stencil. When you are carving chips, you use extreme ultraviolet light to etch patterns into the silicon.
Okay, light etching.
But you need a stencil so the light only hits the right spots. The mask is that stencil. It is a physical blueprint.
Got it.
TSMC handles the creation of these incredibly complex stencils.
And what about the process libraries?
Process libraries are essentially a menu of pre-solved physics problems.
Pre-solved.
Yeah. If an NVIDIA designer wants to place a specific type of memory cell on their chip, they don't have to invent the physics of how that cell interacts with the silicon.
They just pull it off the shelf.
Exactly. TSMC says, here is a digital blueprint for a memory cell that we have already tested 1 billion times. We guarantee it will work perfectly in our factory. Just drag and drop it into your design.
Oh, that's brilliant.
By providing these libraries, TSMC ensures that when those 12,000 different designs arrive at the factory, they all speak the exact same physical language.
So they aren't reinventing the wheel 12,000 times. They have built a universal grammar for chip manufacturing.
Exactly, a universal grammar.
And that feeds perfectly into the second layer of the machine, which is called learning density.
Right.
Because TSMC isn't just mindlessly stamping out 17 million identical widgets. Every single one of those 534 customers brings a unique, excruciatingly difficult problem to the factory floor.
Consider the diversity of those problems. Apple comes to TSMC and pushes them to their absolute limits on system optimization and power efficiency.
Right, because an iPhone has a tiny battery and can't overheat in your pocket.
Exactly.
Hmm.
But then NVIDIA comes in and pushes entirely different constraints regarding massive computational throughput and heat dissipation for artificial intelligence training.
Completely different physics problem.
And then automotive companies come in demanding extreme reliability, requiring chips that won't fail even after 10 years of enduring freezing winters and boiling summers.
So in the old IDM world, a company like Intel only learned from its own internal projects.
Right. If Intel wasn't building a mobile phone chip, Intel's factory didn't learn how to optimize for mobile power efficiency.
They were blind to it.
But TSMC doesn't see Apple, NVIDIA, and automotive companies as isolated, separate projects. They see them as adjacent data points flowing into a single, centralized manufacturing knowledge base.
I love analogies, so think about it like this. Imagine a master chef who decides to open a kitchen, but they refuse to write any of their own recipes.
Okay?
Instead, they invite the 500 best recipe writers in the entire world to bring their secret dishes to be cooked.
I see where you're going with this.
One writer from France teaches the chef a revolutionary way to temper chocolate. Another writer from Mexico forces the chef to learn a completely new technique for searing at extreme heat.
The chef is learning from everyone.
Exactly. The chef absorbs every single secret technique from every single writer. Suddenly, the chef realizes that the heat-searing technique from Mexico can actually be applied to solve a problem with the French chocolate.
The cross-pollination.
Right. The chef is combining these lessons into a level of culinary mastery that no individual recipe writer could ever possess on their own. Apple teaches them power efficiency, the car companies teach them durability, and then TSMC applies that collective, accumulated wisdom to help NVIDIA build a better AI chip.
They become the nexus of all human hardware knowledge. The cross-pollination of knowledge is the real product.
Wow.
And that accumulated wisdom leads us directly to the third layer, reinvestment. Because this knowledge isn't theoretical, it generates massive, almost incomprehensible amounts of cash.
Let's talk about the money.
Looking at the financials for 2024, TSMC generated 2.89 trillion new Taiwan dollars in revenue, with 1.17 trillion in net income.
Trillions.
But what you have to understand is that this isn't just a scoreboard of profit meant to sit in the bank account. This is the heavy fuel for the engine.
It's a cash engine that constantly reinvests into process technology. Let's put that reinvestment into perspective. We briefly mentioned the machines that print these chips, the extreme ultraviolet or EUV lithography machines.
Made by a company called ASML.
Right. These aren't just expensive tools. A single EUV machine costs hundreds of millions of dollars.
It requires multiple 747 cargo planes just to ship it.
And TSMC buys them in bulk. They take the profits from solving yesterday's impossible problems and immediately spend it on building the infrastructure required to solve tomorrow's impossible problems.
The barrier to entry just gets higher and higher every single day.
Which brings us to the fourth and final layer of the machine, ecosystem lock-in. Because TSMC acts as a platform.
A very sticky platform.
Once a Fabless company has optimized its multi-year roadmap around TSMC's specific process libraries, switching away from them isn't like switching the brand of paper in your office printer.
No, not at all.
It's not a simple procurement swap where you just call up a different factory and ask for a better price.
It's an architectural nightmare. I was reading about something called packaging flows.
What's that?
In the past, packaging a chip was simple. You just put a plastic cover on it and wired it to the board, kind of like putting a stamp on an envelope.
Simple enough.
But today, packaging involves stacking multiple different chips on top of each other in three-dimensional skyscrapers, wiring them together microscopically.
Like a high-rise of processing power.
TSMC owns the proprietary methods for stacking these chips.
Yeah.
If you decide to leave TSMC for a competitor, you essentially have to tear down your skyscraper and redesign your entire architecture from scratch to match a different manufacturer's distinct physical rules.
You are locked into their physics.
Exactly. So you have this self-reinforcing loop that is just a juggernaut.
It just keeps spinning.
You serve more designers, which means you see more problems. You solve those problems at a massive scale, which improves your production yields.
Right.
That improved yield attracts even more advanced designers who bring even harder problems, which generates more cash, which you reinvest into new machines. Wash, rinse, repeat.
It's brilliant.
If we connect this to the bigger picture, It fundamentally changes how we should view a factory.
How so?
The fabs matter, of course, because they produce the physical objects, but their real value is that they are classrooms.
Classrooms, I love that.
They are the physical environments where the entire global semiconductor industry pays TSMC to teach them what is hard, what is breaking, and what matters next.
Okay, so they have built this flawless machine. They have become the trusted, neutral clearinghouse for the entire digital world.
Yes.
But usually in the tech sector, when a company builds a massive information edge, it gets ruined because competitors eventually figure out the formula and copy it.
Right. Someone looks at your software, writes a better version, and undercuts you on price.
Exactly. But TSMC's wall, the ultimate barrier they eventually hit, is entirely different. And frankly, it's a bit frightening.
It is.
Their core problem wasn't that they were being copied. Their problem was that they were too successful, to the point where they made the entire world highly uncomfortable.
The competitors certainly exist. Companies like Samsung, Intel, Global Foundries, and UMC all apply competitive pressure in various ways.
Sure, they are all trying to catch up in the nanometer race.
They are. But the profound existential challenge facing TSMC today isn't about whether Samsung can etch a slightly better transistor in a lab.
It's much bigger than that.
The challenge is systemic and geopolitical. It is the danger of concentration risk.
Right. Because TSMC executed their strategy so perfectly, they became the indispensable manufacturing nexus for the most advanced technologies on Earth.
Indispensable is the perfect word.
And suddenly, governments and massive corporate customers woke up, looked at a global supply chain map, and realized the absolute fragility of a single-point failure.
It was a very rude awakening for a lot of people.
If all the advanced chips for smartphones, AI infrastructure, and military applications are flowing through a handful of fabs clustered on a single island in Taiwan,
That is a strategic bottleneck that keeps prime ministers and CEOs awake at night.
the success of the model created a terrifying geopolitical vulnerability.
And that realization triggered a massive tectonic shift in the industry. We are no longer just looking at a business case study. We are looking at the politicization of an information edge.
So how did they respond?
TSMC's response to this immense pressure is forced geographic diversification.
They have to spread out.
They are currently building fabs in Arizona in the United States, a facility called JASM in Japan, Nanjing in China, and a specialty fab in Dresden, Germany. They are attempting to export the machine.
But I have to ask a serious question about this because from everything we just discussed, it feels like a massive contradiction.
How do you mean?
If the magic of TSMC was this incredibly dense, centralized learning environment, this one island where all the suppliers, all the chemical pipelines, all the engineers, and all the accumulated routines are packed tightly together, constantly cross-pollinated.
Right, the density.
Doesn't literally copy-pasting these fabs across the globe dilute the very information edge that made them special in the first place?
You have zeroed in on the exact friction the company is navigating right now. This is the hardest transition they have ever faced.
It has to be.
You can pour $40 billion into the Arizona desert and build a state-of-the-art building. You can buy the exact same ASML lithography machines and plug them in.
But it's not the same.
But a fab is not just a building and a machine. It is an organic system. It is incredibly hard to replicate Taiwan's dense supplier network.
Because in Taiwan, if a specialized chemical pump breaks at 2 a.m.,
The supplier is 30 minutes down the road and arrives with a replacement immediately. In Arizona, that ecosystem has to be built from scratch.
that's a massive hurdle.
Furthermore, you're trying to export accumulated manufacturing routines and a specific culture of execution merely by decree.
Which is almost impossible.
The Taiwanese engineers are used to a culture of working around the clock to solve yield issues. Integrating that with different labor cultures globally is a monumental task.
So it's not a seamless copy-paste.
Not at all. Building abroad is deemed strictly necessary for global supply chain resilience, but it does not instantly reproduce the learning environment.
It's a completely different game now. They aren't just managing the physics of silicon anymore. They're managing international relations, labor unions, and global logistics networks.
The company is now forced to balance pure process leadership against diplomacy and the varying industrial policies of different nations.
Right. And just to report factually on what the sources say about this dynamic, governments around the world, whether in US, China, Europe, or Taiwan, are instituting sweeping policies.
Offering massive subsidies.
Right. Based entirely on their own strategic needs regarding supply chain security. The factual dynamic we are observing is simply that hyper-concentration led to intense state scrutiny.
Which forced the need for geographic resilience.
The sheer gravity of their success pulled the geopolitical world into their orbit. We're just looking at the mechanics of the choke point here.
Exactly. The world isn't trying to route around TSMC because the Foundry model failed. They are trying to route around the geographic concentration because the model succeeded almost too completely.
It is the ultimate validation of Morris Chang's 1987 insight.
It really is.
The neutral intermediary became so vital, so deeply embedded in the fabric of human progress, that it transcended economics and became a matter of national security for multiple global powers.
Quite the evolution from a startup foundry.
So what does this all mean for you, the listener? We love zooming out from the specific story of one company and looking at the broader laws of the technology ecosystem.
The bigger picture.
Exactly. How can you apply this mental model to other industries? Because the profound truth that TSMC reveals is that the most valuable information edge often belongs to the neutral intermediary, not the flashy product company with their name on the billboard.
Apple absolutely knows more about the internal software of its iPhone than TSMC does.
Yeah.
NVIDIA knows vastly more about the mathematical architecture of its AI chips than TSMC does. But TSMC knows something none of those giants can ever know alone.
Which is?
They know how the entire frontier of the industry is evolving simultaneously. They don't own the endpoints, but they own the specific intersection where all those endpoints become legible to one single system.
There are a few really powerful transferable lessons here that I want to tease out because they are mind-expanding.
Let's hear them.
The first is that in certain environments, neutrality is actually more powerful than vertical integration. If you are looking at an industry where participants are terrified of being exploited by a supplier, say, cloud computing or logistics, the player who can establish ironclad, trusted neutrality will absorb all the demand.
And this reframes how we should think about physical assets. Massive industrial facilities are not just capital assets sitting on a balance sheet depreciating over time.
I'm alive.
They are knowledge institutions. Every single process generation, every physical iteration encodes lessons from thousands of customer interactions.
It also proves that scale fundamentally changes visibility. If you are a small boutique manufacturer, you just make things.
Right.
But if you are a dominant scaled manufacturer, you start to detect cross-industry patterns that your own customers can't even see. You become an oracle.
And perhaps the most surprising takeaway in our modern era is the concept of physical lock-in.
Physical lock-in. Let's dig into that.
We are so conditioned to think that only software platforms with their frictionless network effects like a social media app or an operating system can compound and lock in users.
Because switching costs are high in software.
Right. But TSMC proves that a physical platform, made of atoms rather than bits, can compound just like software. Their sticky features aren't lines of code. They are physical process nodes, packaging flows, and production reliability.
And of course, the lesson that ties back to our geopolitical discussion. A choke point becomes a strategic, uncomfortable liability long before it stops being profitable.
Once you become the bottleneck for human progress, governments get very interested in your business model.
Are there other companies out there right now operating on this same wavelength? Because once you see this pattern of the neutral intermediary, you start looking for it everywhere.
There are two fascinating modern parallels that help solidify this mental model. The first is actually within the same industry. ASML, the Dutch company we mentioned earlier that builds the extreme ultraviolet lithography machines.
Right, the massive cargo plane machines.
Exactly. They also sit at a crucial singular layer of the industry. They learn from serving the most advanced manufacturers, taking feedback from TSMC, Intel, and Samsung to make their next multi-million-dollar machine even better.
So they are learning from everyone, too.
Yep. The difference is that ASML's bottleneck is the physical complexity of the equipment, while TSMC's bottleneck is manufacturing execution and ecosystem trust.
And I was thinking about a parallel that isn't even in hardware at all. Think about Bloomberg in the financial sector.
Oh, that's a great comparison.
Every individual bank, every hedge fund uses the Bloomberg terminal for its own specific workflows, its own proprietary trading strategies. The hedge funds don't share their secrets with each other.
Of course not.
But Bloomberg, as the neutral intermediary providing the data pipes, gets to see how the entire global financial system communicates. They see the whole board.
That's exactly it.
TSMC is basically doing the exact same thing, but instead of routing financial bits, they're routing physical atoms.
If we connect this to the bigger picture, for investors, for builders, or for anyone analyzing an industry, The central thesis is clear. Collecting learning is exponentially more powerful than just collecting revenue.
Revenue is just cash.
Revenue is a one-time transaction. You sell a chip, you get $1.
Right,
But learning compounds.
right.
If you can become the trusted layer that everyone must pass through, the knowledge you extract from user A automatically makes the system better, faster, and more efficient for user B.
It's like being the builder of the town square versus being a merchant in the square.
I like this.
The merchants are out there screaming, fiercely competing, trying to sell the best apples or the finest silk, and they might make a great profit on any given day.
Sure.
But the person who owns and maintains the cobblestones of the town square itself, they know exactly how the entire regional economy breathes.
They see the big picture.
They know the foot traffic patterns, they know who's buying what, they know the macro trends before any individual merchant does.
And because they never sell their own apples or silk, all the merchants trust them to keep the gates open.
That's the key.
TSMC won the semiconductor war not by designing the most important chips, but by becoming the one unignorable factory that every important chip company was forced to teach.
What an incredible journey we've gone on today. We started by looking at an industry that was trapped in a vertically integrated straitjacket where brilliant, world-changing ideas were dying on whiteboards because designers couldn't afford a billion-dollar factory.
And they couldn't trust the massive legacy manufacturers who already had them.
We saw how Morris Chang's single paradigm-shifting insight in 1987 about the power of absolute neutrality liberated that talent.
Paving the way for the Fabless revolution that gave us the modern smartphone and the AI boom.
We explored how that unwavering trust built a 17 million wafer learning machine that compoundingly reinvested its knowledge into an insurmountable physical lead.
An absolute juggernaut.
And finally, we saw how the ultimate prize, total market indispensability, brought the massive unintended consequence of global geopolitical scrutiny.
It is a masterclass in long-term strategy, immense patience, and the profound value of understanding where the real structural leverage in a system actually lies.
And as we wrap up this deep dive, we want to leave you with a final thought to mull over as you look at the business landscape around you.
Okay, what is it?
If TSMC proved that a massive, heavy physical platform made of atoms can compound knowledge and create a defensive moat just as effectively as a digital software platform made of bits,
Right.
what other heavy, physical, unsexy industries out there are currently trapped in their own vertical integration? What other industries, whether it's energy grid management, biomanufacturing, or aerospace, are desperately waiting for their own neutral foundry revolution?
It's a question that, if answered correctly, could identify the next great structural shift in the global economy.
Thank you so much for joining us on this deep dive. We hope it gave you a completely new lens through which to view the technology you use every single day. And as always, we warmly invite you to keep questioning the structures of the world around you.